Hi, there were some people who wanted me to take a closer look at the Energy Micro Tiny Gecko board. Power it up, hook it up, do some measurements. Sounds like a good idea. Let's go. Now there were a few people who commented on the mark on the LCD here. It's not a mark at all, it's just the ta-da! The plastic film protecting the display. Now let's actually power the thing up and see what happens. Woohoo! Get latest software from EnergyMicro.com. Not too keen on the segmented display here. Oh, it's got a nice little fancy target display there, custom display, and it's jumped straight into what looks like the CapSense slider thing. So let's play around with that. Well, hey, yeah, it does work. Let's touch it over here, and you'll notice that that dash disappears, and then it's giving you a count, which is presumably the count position on the slider. And if I slide my finger along there, not only does that bar graph, rotational bar graph go up, but CapSense Touch also goes along. It scrolls the text. CapSense Demo. It's a little bit touchy, pardon the pun, but you can see that works a treat. And if you push the button here, you end up in a slider thing, which actually, well, it slides the segments along the display like that instead of scrolling the text. And if you do it again, it's got looks like pad 0, I assume refers to that pad, and you can see the value change. And if I touch these pads over here, it doesn't really change at all, and I can swap between pad 1. If I touch pad 1 there, the value changes. If I touch pad 0, it doesn't really change that much. So there you go. It looks like it comes preloaded with only a CapSense demo. It could have something else, but I can't find it. There's one thing I didn't see in the original look at this was this LC sensor here. It's a little inductor, and it can detect nearby magnetic fields. And but don't get too excited. You're not going to be able to take this thing out and find Lassiter's Reef or anything like that. It's only got a detection range of a couple of millimeters, I believe. And I did complain that there wasn't a gecko on the board, and sure enough, previous versions of the board have had a gecko, but the one I've got, they've taken it off. But on the chip there, you can see, cute little gecko, laser etched onto the chip. I love it. And this switch down here turns it off and on from the battery power. But let's hook it up to the USB and see what we get. Ta-da! Ping! And it powers it alternatively from the USB. And we've got our Sega J-Link debugger LEDs going there. So let's give the software a try. And the only documentation you get in the box is this quick start guide, which says go to energymicro.com/simplicity. Well, let's give it a try. And bingo, you type in energymicro.com/simplicity and you get this page, a step-by-step procedure to run the software. Looks pretty easy. Let's give it a try. And here it is, Simplicity Studio, free download. And it appears that they've got different demo boards. This is the Tiny Gecko, but they have other ones with large RGB type displays on them, and looks like the software would support all of those. So let's download it, and there's a whole bunch of demo programs. Beautiful. Let's give it a try. And I won't bore you with the entire download process. It was a 7 meg download, very reasonable size, and it popped up with this: the following recommended packages are not installed. Do you wish to install them? Better. On second thought, screw that, it's taken too long, so I'm going to cancel that, and I'll see what happens when I plug in the board. And it looks like you have to install everything, so don't just do what I did and cancel it. Make sure you install all the options. And here we go, we get the EnergyAware stuff, because this Tiny Gecko board actually has any energy measurement built in. It's effectively got like a little microcurrent built into it. It can it has two different ranges that can actually record the CPU measure and transmit back and graph the CPU current for various ranges and power cycles. So we'll give that a try, and we've got app notes, we've got examples, kit documentation, demos, videos, all sorts of things. Looks pretty good. Here's all the documentation, so let's take a look at, and there's not much on the data sheet, but it does tell you here it has 0.1 microamps or 100 nanoamps to 50 amps measurement range of measures the voltage and the current of the VMCU rail, so that measuring voltage and current allows you to calculate how much power, because the thing with measuring and characterizing and comparing the power consumption of different microcontrollers is just that you have to do power. You can't necessarily go on just the current figures because it's dependent upon the supply voltage. Let's take a look at the user manual here. It's 41 pages, seems fairly comprehensive. And if we take a look at the block diagram, there's the segmented display. Look at the tiny little gecko. They've got a gecko symbol on the display. Haven't figured out how to get that one up yet, but that's nice. It's got a little battery bar graph and the various circular things, plus the segmented display as well, and like a timer display up here too, and there's milliamps, microamps, so maybe if we run some of the power demo apps, it'll actually tell us how much power's being consumed. That'd be really nice. And there's the rest of the block diagram, the touch slider, a couple of push buttons, the ambient light sensor, the LC sensor as I mentioned, and some debug stuff, and the optional op amp, and that's about it. But what I'm really interested with this thing is the power management capabilities. And if we click on the demos button here, what do we get? We get a whole bunch of demos, and there's here we go, a demo of different energy modes. Let's have a look at that. So here it is. They've got the instructions here. It basically, you just cut and paste this example code here, a tiny amount. You just put it in your main thing, call up this function once by the looks of it at the start, and it looks like it gives you the energy profile of the different functions. Look at that. Main is taking 98% of the power, I'm assuming. Yep, energy in microjoules. There it is. And that's brilliant. And presumably, if you've got a big complex app, you can see which functions are taking the most amount of power. I'm really liking this, because doing this sort of stuff with a regular microcontroller which doesn't have the built-in support for doing something like this is usually very difficult and ad hoc. You've got to know how much instruction time is spent in each subroutine and function, and then try and measure your battery consumption. But here you can actually do it directly on the demo board. It looks pretty trivial. Wow, this is powerful. Now what I did is I clicked on the main function, and this looks like the demo program it's running, emode.c, and you can see the code in here, and it's drawing down the bottom here 5.92 milliamps at 3.3 volts, but I don't, offhand here, I don't know what frequency that's running at or what it's actually doing at the moment, but you can actually, it looks like you can go in and you can debug your code directly in this EnergyAware profiler window. And if you go into the EnergyAware battery thing here, it gives you a tool which allows you to estimate the battery life of your program. I'm running a demo here, and it's a CR. You can choose your cell, alkaline AA, AAA, or your CR2032s, for example, lithium cells, number in parallel, number in series, and it can apparently give you a profile, boom, of there's the battery curve like that, and it can show you the minimum, where you set your minimum operating voltage at. Presumably you can change that figure. Average current might be 2.8 microamps here. Estimated system operating time, 8 years. There you go, the rated capacity is on. That's a CR2032 cell, 8 years at 2.8 microamps. That's rather neat. You'd have to, like, you can actually presumably load in your actual program, and it will actually estimate it based on your real application. I'm just running one of the simulation demos here, but this looks really neat. They've really put a lot of effort into energy management on these Gecko microcontrollers. It seems to what actually sets them apart. So I like this. Man, this is neat. I think I might, this is kind of swaying me towards using an Energy Micro device in my MicroWatch Mark II, I think, just because the tools are neat. And if we go into the EnergyAware Designer program here, this allows you to generate C code, the initialization C code for various packages and various peripherals and things like that. So you go up here, you choose your device from all those and all the different types of packages, and then we can enable things like enable our real-time clock. Bang. We want to do that. We want some ADCs. Yep, we've got, looks like 4 to choose from in this particular package. Let's enable, 4 channels of those. And, oh yeah, I2C. I want one of those. And looks like you can get 3 different pin locations for the, yeah, there we go. You can select which pins you want. Oh, neat. I like that. And, oh, actually, it tells you it conflicts. I am assuming the red means that they've conflicted with something else. Excellent. All right. I like that. Otherwise, let's put them up here, and we enable that, and you can do that with any of the internal peripherals. We've got the timer, the interrupts, and stuff like that, and you can generate PDF reports for this sort of thing. We can do the, we can show pin matrix views. There we go. That's a matrix kind of view. Once again, we can save the PDF for that. It's got a button down here, but let's get out of that and let's generate our C code. Bingo. There it is. We've got our C code for initializing this particular device. Looks like it's set up as 14 megahertz high frequency clock, GPIO. There's a the PIOs, open drain with pull up and filter and all that. There's the ADC, the I2C. All your initialized code is there for you. I've got to say that is one of the better configuration tools I've seen from any vendor. That's very nice, because a lot of the pain involved with microcontrollers is just getting the damn things up and running and getting the modules enabled, because you first write your program and then, it doesn't work first go and you're scratching your head wondering why, because you haven't enabled some pin or some register or something like that. This just allows you to do it in a nice graphical user interface and make sure you've got it right. Neat. And let's try out the EnergyAware Commander option, which apparently allows you to download firmware and do stuff like that. So let's connect. We're connected to our Tiny Gecko starter kit, wherein we can go to various debug modes, USB address, the chip type we've got on the board there, the chip revision. So it's read the silicon ID code out of that. We can flash in, there we go, we can flash in various stuff. So that's like a little programmer. Is it? That's almost like a standalone programmer option, I think. So let's go look in the demos. There we go. We can download the demos, blink the LED. Woohoo! Try different energy mode demo using the LCD. Let's try that. Start. And it resets. And that's pretty quick. And yep, we've got something on our LCD. When you press the reset button here, you can see that it's in 32 megahertz mode, and you can actually cycle through different modes, 32 kilohertz crystal, and when you do that, plus the RTC, the real-time clock, so you've got all these different modes that you can measure, and in the background you'll be able to see the graph changing. So let's give that a try. So let's take a look at that. You can see it's drawing 5.92 milliamps now because it's in the 32 megahertz mode. So that's what it's drawing at 32 megahertz, almost 6 milliamps at 3.3 volts. But if we change that mode, we can see it. Let's go to 32 kilohertz and see what happens there. And bang, it's dropped. And you can see all the different functions down here where it's taking the power consumption for this application. All right, this is really cool. Check this out. I'll switch it to 32 kilohertz mode. There it is. And you should find the current consumption, bang, drops all the way down to 1 microamp because we've got that logarithmic scale there. And if I choose the RTC plus LCD option here, there it is, it'll leave the LCD on, and there we go. It takes about, I don't know, 6-7 microamps or something like that to drive that segmented LCD plus plus to have the 32 kilohertz real-time crystal working at the same time. The touch slider doesn't seem to be active there at all, but there you go. That's how much energy is required. Oh, you can see if I press the button, there we go. You can see just the slight increase in energy consumption, and you need to take that into account in your designs. If you've got a low value pull-up resistor on your switch and the user's pressing that, it's taking a little gulp of current every time you actually do that. So you really have to optimize the value of your pull-up resistors on those user switches. And if we go and take a look at the application notes here, they're fairly comprehensive. Like there's FAT on an SD card, Ethernet, all the good stuff, AES cipher modes, and all sorts of things. There's low energy UARTs. I like it, but let's go in and actually see. And here's a list of the 5 different energy modes we saw in the example demo that we were just running. So mode 0 is where these CPUs run in flat chat, and it's just everything's chewing as much power as possible. And then there's sleep mode, energy mode 1, where basically the CPU is disabled, but any of the peripherals using the, here we go, wait for it, the peripheral reflex system, PRS, woohoo, and the DMA, it can actually do autonomous operations without powering up the CPU. For example, the timer may repeatedly trigger an ADC conversion at a given instance. When the conversion is complete, the results move to DMA to RAM, and when a given number of conversions have been performed, the DMA then wakes up the CPU using interrupt. So you can basically data log, by the sounds of it, data log things from the ADC without using and powering up the CPU at all. Brilliant. And then there's deep sleep. And energy mode 2 means that there's no high frequency clocks running at all, only like the low power 32 kilohertz clock for doing I2C stuff, LCD operations, UART operations, analog comparators, real-time clocks, and some basic GPIO check-in. And mode 3 is the stop mode, and that differs from sleep mode in that no oscillator apart from the watchdog is actually running at all, even the low frequency one. So even in this mode, you can still do an I2C address check. Watchdog, of course, you can do pin interrupts, analog comparators, and GPIO interrupts without any internal clock running. And energy mode number 4 is complete shut-off mode, where it can draw, so they claim, as little as 20 nanoamps, and the only way to exit that mode and get back to operation is to trigger the reset line or cycle the power. But this claim of 20 nanoamps, I think we might be able to check that. Now, as a bit of a industry comparison here, I've got it running in the LCD plus RTC mode. So trust me, the LCD is actually displaying something here, and it's running the real-time clock as well. And as you can see, it's drawing around about 5 microamps or something like that, because remember, this is a logarithmic y-axis here. But if we compare that 5 microamps running with, say, a microchip PIC32MX series micro, so I'm comparing a 132-bit micro to another, not quite apples and apples, but reasonably close. In the low power RC mode at 32 kilohertz, it's going to be drawing roughly 100 microamps typical at 3.3 volts. So this thing's driving an LCD as well as running the real-time clock, but I guess the processor's not continuously running at 32 kilohertz here, but you get the idea of what you can actually do with just 10 microamps or something like that. There's hardly anything being used there at all. Sniff of an oily rag. And of course, if you put the demo in energy mode 2, which claims on the LCD that it's 32 kilohertz, so I presume the processor's running at 32 kilohertz. It may not be running continuously, but as you can see, it draws under 1 microamp. Amazing. And if we use energy mode 2 with the real-time clock turned on, you can see it's now just a smidgen on or a smidgen over 1 microamp. And again, if we choose the PIC32 MX Series Micro as an industry comparison for an equivalent 32-bit micro with the real-time clock plus the timer one with the 32 kilohertz crystal, there we go, 23 microamps typical, 50 microamps max. So the Energy Micro, using its ARM Cortex M3 plus all its energy management capability, low power stuff, it draws at 1/23 of that, only 1 microamp. And I've put the board into energy mode 4, which is complete shutdown mode. And as you can see, we're down in the noise, under 100 nanoamps there. It's not really accurate down here. It might be, say, 10 nanoamps average, but really it's not accurate at all. So let's see if we can get some more accurate measurements of that. And if you read the user manual here, it actually tells you what it's capable of measuring. Here it is, from 0.1 microamps to 50 milliamps, and does that in 2 different ranges, and it can go down to 100 nanoamps resolution, but resolution's different to accuracy. But the built-in power measurement capability, you know, it's probably good enough for most applications, but I think we'll just double check that and see if we can measure it ourselves. And if we take a look at the schematic here and see how it's doing the MCU power current sense, this is the circuit. It's using our Linear Technologies LTC 6102 zero drift precision current sense IC. In fact, it's got 2 of them, one for range 1 and one for range 2 as well. And it's not a bad device at all, and it's a current sense amplifier. And if we take a look up here, we've got an LP3982. That's a low dropout voltage regulator for the supply for the CPU, and 5 volts in, 3.3 volts out. And there's our current shunt resistor, the 4R7 there, and of course it taps off those 2 values down into the current sense amplifier down here for both ranges. And then the output is switched in here. There's our coin cell battery, and our output there goes to our VMCU in there. So that goes to the to a specific pin, which goes onto the microcontroller, which is just for the MCU core. So we can measure the power consumption of that. And by looking at this is some sort of connector or some sort of test pad. If we look at R704 here, 0 ohm resistor, we should be able to get in there and use that. If we desolder that resistor, we should be able to break into that with my microcurrent adapter and actually measure the current taken by the MCU pin. Let's give it a go. And if we take a look at our board here, we can see our 4.7 ohm current shunt resistor there with the 2 resistors going off into the 2 current shunt amplifier chips. And here's our ST700 connector down here, and that's R704. So if we desolder that sucker, we should be able to get in there and measure the current consumption really nicely using this header connector. I love it. And bingo, we now have a current shunt in there. We can just take that out and we can measure our microcontroller power consumption. They were thinking when they designed this, because it's Energy Micro and they want you to be able to measure the energy that this micro is using. Go figure. And what I've got here now is my microcurrent on the milliamp range at the moment, hooked in, jump it into that current shunt header connector up there, and I've got the output connected to the Fluke on millivolt range. So 1 millivolt equals 1 milliamp. So it's drawing 4.8 milliamps at the moment, and that's in its default 32 megahertz mode. So if we let that go down, it's 2.8, switches off, bang, it goes into the mode. So we can measure the different modes now by just cycling through and selecting the mode we want. Let's go to that 32K range mode, go down there, and let's measure the consumption of that. We're only talking, there it is, that 1 microamp. But of course we can get much better resolution on that just by switching to our nanoamp range down here and then taking it up, and bingo, there we go, 990 odd milliamps is jumping around. We could smooth that out if we wanted to, but it's drawing around that 1 microamp figure. Now of course the big question is, what happens in that power mode 4 where it's completely shut down? Well, we'll find out in a second. Bingo, it's dropped down to nothing. Let's switch this down to our nanoamp range, and 1 millivolt, it's drawing, nah, that's a bit disappointing. It's drawing 100, oh no, it's going down, there we go. So obviously something is charged up there, and it's got to go down. So I might wait a bit and see what that gets down to. And there you go. When we power it from the USB input like this, it actually enables the some of the energy management stuff and some of the analog switches and things. So you really need to power it from the USB to get that capability. And there we go. It's about 165 or 160 odd nanoamps power consumption. Energy Micro claim around 20 nanoamps in energy mode for that complete shutdown mode. So I decided to have a look at the schematic again and see what is on that VMCU pin. And it turns out, there it is. There's another device on there. It's a TS3A4751, and that's a Texas Instruments single supply quad analog switch. And if you go down here and take a look at its current consumption, there it is at 25 degrees C, which is it's near enough to that here in the lab. It's around about, well, no, actually it's saying that's a maximum figure there, a maximum figure of 75 nanoamps. So, you know, but that could vary quite significantly, I'm sure, but at least a good part of that current is coming from this device. So then what that's doing is powering this analog switch here, which has the JTAG signals going through it. So I'm not sure why they're powering that device. Well, I guess you've got to measure, it allows you to measure the MCU power consumption during JTAG debug operations, I suppose. But there you go, there's the VMCU target and the VMCU debug. There are the things that go down and power the microcontroller. So it looks like that's a bit of, I don't know if it's not really an oversight, I guess, but it's just a design thing that doesn't allow you to accurately measure just the raw core power consumption of this thing. And bingo, I hate these multi-sheet schematics. They're rather confusing, but VMCU not only powers this analog switch here, but there's another analog switch. Here it is, VMCU, also powers U695B there, so there's another device. So there's two of those devices there at 75 nanoamps maximum, which brings us to 150, and we're measuring 160. So really, it comes out in the end. It works. The micro is around about 20 nanoamp, 10 or 20 nanoamps or so, according to the data sheets. But this isn't going to be very precise because you've got you're measuring the power consumption of these devices as well, these analog switches, which is going to vary with temperature, and the micro is going to vary with temperature as well. So unfortunately, that jumper on there does allow us to measure the current, but there's that residual in there. It allows you to measure the current of your micro under test, except for that very deep sleep mode where you can't really characterize the 20 nanoamps. What a bummer, but I'm sure it will actually meet its spec. I'm sure they've done their homework and they've done their isolated measurements there, but that's still handy for developing your applications, just using that jumper shunt there, and you can measure the in-circuit current, or you can do it using the onboard energy management thing. So there you go. I rather like that. That's a bit of playing around with the Energy Micro EFM32 Tiny Gecko starter kit, and I think I like these devices. They live up to their name, Energy Micro. They're all about measuring the energy consumption and different energy modes of these microcontrollers. So next time you're in the market for one of these for a low power micro, check them out. That's Energy Micro. So if you liked the video, please give it a thumbs up, and you can discuss it all on the forum. Catch you next time. And this is rather neat. I've got it in LCD mode here, and I disconnect the power, break it, and it fades away a bit because it's still storing energy in the bypass caps, and that's what's still powering the circuit. It still keeps it alive for quite a few seconds, and even when you think it's dead, it can come back. Beautiful.